Hello everyone, my name is Tyler Jankowiak from Beta CAE Systems US. This video is an overview presentation and demo of the OptimWeld's multidisciplinary spot weld optimization tool. To begin with, the motivation behind creating the tool was because current approaches to optimizing weld locations are lacking proper capabilities. Typically, it's a tedious and time-consuming process of manual trial and error, or parameterized spot weld lines are used which require many simulations to find an optimum. Overall, the current methods are inefficient and ultimately lead to higher production costs and manufacturing delays due to poor placement of welds. So we wanted to create a new automated process that's more powerful and efficient than what's currently available, as well as user-friendly. By using the process we've developed, the number of welds placed on an assembly can be quickly reduced, subsequently lowering manufacturing costs and increasing production speed. The main idea of the tool is to take an assembly or full vehicle model with a large number of uniformly distributed welds and optimize it to find a more efficient, non-uniform distribution with fewer welds, while still meeting our performance targets. This is achieved by performing a combination of spot weld line optimization along with selectively realizing welds in specific locations that are critical to model performance. In terms of general capabilities, the tool was built to be multidisciplinary, so users can run crash, durability, and NVH load cases in parallel and find the best distribution of welds for these cases at the same time. Through the use of critical welds, we're able to reduce the number of design variables used in the optimization, leading to a reduction in simulation runs needed before an optimum design is found. All of this is accomplished through the OptimWeld's user interface within ANSA, which uses a streamlined approach to quickly prepare the model, generate the optimization workflow, and process the results. Steps are taken with the tool to ensure that designs created during the optimization would be feasible in reality. This includes allowing the user to specify a value for the minimum distance they would like between their welds to ensure the design is manufacturable. Additionally, weld lines can be marked as symmetric, which ensures the weld locations for symmetric parts are always mirrored. In case there are any welds that are deemed necessary for production of an assembly, they can be set as manufacturing welds that will remain at a specific location throughout the optimization. Users can freely model their load cases as normal without restriction on weld representation or sheet stackup. The OptimWeld's interface is made as a plugin inside of ANSA and is designed so that the entire weld optimization process can be completed from start to finish without ever having to leave the ANSA window. And now for a demonstration. I'll start by opening the tool and specifying a project directory. I'll set the baseline number of welds, which right now is taking the initial number of spot weld points that I have in my model. And what I want to do next is create weld lines, and these weld lines are going to represent the design space for the optimization. What I would do is identify symmetry, and what this will do is automatically detect the symmetric parts in the model according to a certain matching percentage. In this case, symmetry is already defined. And now I will start picking the connectivity groups on the screen and isolating them. And here I can use these functions to convert the existing spot weld points into spot weld lines, which are going to represent my design space. When I'm satisfied with the lines that I've created, I can pass them, which will mirror the created lines to the symmetric side of the vehicle. This saves a lot of time in that I don't have to duplicate work for the symmetric parts, as well as allowing any symmetric welds to be created during the optimization to be reflected automatically. Along with automatically converting the connectivity group, I can manually select a group of points that I want to create a line from, in case I come across an area where I don't necessarily want a spot weld line for that connectivity group. I'll continue using these functions until all of my candidate areas have been converted to spot weld lines, at which point I'll move on to grouping the lines. Now with all of my lines created, I'll begin the grouping process. And this is what assigns design variables for the spacing of these spot weld lines. And the spacing is going to be varied for every design throughout the optimization. And when I'm selecting these groups, I want to pick them according to location on the vehicle. And this is going to help the optimizer determine the proper spacing values that should be used for each of these load cases. So I'll give a name for this group. I'll hide it from my screen, so I'm left with the remainder of the ungrouped lines, and I'll group them as well. At this point, all of my lines have been grouped. The next thing I want to do is apply a split to these groups, which is going to separate the groups that I've made according to the length of the spot weld lines. And this will give the optimizer fine control over short lines. Next, I'll specify the spacing ranges that I'm going to use for the short and long groups. And then I can close this window. Next, I can create my optimization task. This will take the groups that I've made and assign the design variables for them. And here is where the spacing has been parameterized. So during the optimization, the spacing will be varied for each of these groups, and the model is going to be output and sent to the solver. The last thing I will do is set the output file name for this file, and then I can save this. This file is ready to run for my optimization. In case I have other models in my optimization, I would want to output a common model file, which is going to take my spot weld lines and the optimization task that I created and output them to a separate ANSA database. So then I can merge the lines and the optimization task into that file so that my lines are consistent across all of my load cases and I don't have to duplicate the work that I just performed to create these lines. In this case, I only have one load case, so I'll move next to the load case definition tab and fill out the required information for my load case. I'll give my ANSA database, which is my baseline model that's ready to run. This is the file that's going to be used throughout the optimization. I'll give my input file, which is the name of my file that's being output from ANSA. My submission command to send this file to the solver. Next, I have my post-processing file. This file is going to process my optimization constraints as well as the weld information to determine which welds are critical to the performance and should be preserved throughout the optimization. Next is the result file, which is the text file that Meta is going to output, containing my constraint information. And I'll give an upper value for this constraint. In case I have other load cases or other constraints to add, I can click on the respective buttons and increase the number of load cases or constraints in this list. At this point, with everything finished, I can say generate, and this is going to create an LSOPT project file, and LSOPT is going to be used to drive the optimization. If no other work needs to be done, I can say execute and directly start the optimization. Otherwise, I can open up the LSOPT file and do any last-minute adjustments to the workflow if needed. Otherwise, this workflow is ready to run. So like I just shown, the load case setup window is used to take all of the relevant load case information to generate an LSOPT project file, which will drive the optimization process. While the optimization is running, the best designs will be dynamically shown in the report window. And this window will only show the designs that pass all constraints, as well as give a reduction in the number of welds in that design compared to the baseline. Once a design is found that gives a satisfactory reduction in welds, the optimization can be stopped. To test this process, we performed a case study using a simplified vehicle model with 2 crash load cases. For optimization constraints, we set the baseline intrusion values for these designs as the upper limits, with the goal being a reduction in the total number of welds in the model without sacrificing our baseline performance. Once the lines are created, they are placed into groups, which will assign a design variable that changes the weld spacing. We created 16 groups of lines, selected according to their location on the vehicle. So for example, the spot weld lines for the doors are selected together in one group, as they will experience similar loading in the side impact case. We do this because we want the optimizer to be able to properly set the weld spacing for this group, as it will be able to see how the weld spacing in this area influences the intrusion of the side impact load case. The lines are further divided based on line length to give more precise spacing control to smaller weld lines. So we end up with 32 design variables for this case study with over 1,000 spot weld lines. The common connection line model, along with the ANSA optimization task, can be output as a database to be merged with any other load cases that will be part of the optimization. So we take the lines created in the front impact model and merge them into our side impact model. With common connections in all models, we can be sure that the spacing and subsequent placement of critical welds will always be consistent across the models we're optimizing. With the models prepared, we can then move to the load case setup tab, where we provide the information needed for OptimWelds to automatically create the optimization workflow. The workflow begins with LSOPT providing line spacing values for each of the created groups. ANSA will take those values as input, create the welds according to this distribution, then output the mesh file. This model is solved and the results are processed by Meta, which is going to extract the optimization constraint values as well as weld information. The constraint results are used by LSOPT to sample the line spacing for the groups, while the weld information is processed to determine which welds are considered critical to model performance. These critical welds will be recorded and fixed in the same location for the following design, where ANSA gets a new weld line spacing. This process continues until an optimal design is found. Now on to critical welds. Critical welds are welds that are deemed important to model performance according to a user-defined criteria that is processed through Meta. This criteria can be anything that distinguishes it as taking a significant amount of loading during the simulation, whether it's force, stress, material failure, or fatigue life. When a weld reaches this threshold, it's considered critical and will be carried over to the next design in the optimization. For the case study we performed, our critical weld threshold was set to 6,000 newtons. In the case of an MDO, where there are multiple models being used in parallel, all critical weld information and line spacing is kept consistent across all models of the same design iteration. So the front impact load case, which will see many critical welds in the front of the model, will also contain the critical welds around the doors, which came from the side impact model, and vice versa. Now, if we look at a schematic representation, the weld locations are provided only from the spacing of spot weld lines to start. The spacing on these two lines will then be varied for every consecutive design. Additionally, there are some welds that have been selected by the user to be manufacturing welds that will remain at these locations throughout the optimization. If there is a situation where any welds fall too closely to each other, these frozen welds will take priority over other welds, which will then be deleted. Once this design is solved, Meta will process the results to extract the optimization constraints and weld information. All of the welds in the model are checked against the critical weld criteria that's been set, so we look at the maximum force seen in each weld. In this example, we have two welds that pass our criteria, so we'll mark these welds and use them in the next design. So looking at the results of our first design with the marked critical welds, we'll get a new spacing for our second design. And notice that when this happens, we might have some conflicts with the proximity between the welds created from the spot weld lines, as well as the manufacturing welds and the marked critical welds. In this case, those overlapping welds will be automatically found and removed, and this design is going to be solved. After that, we get a new set of critical welds that are found, and we use those critical welds when we create the model for design 3. Design 3 is going to be solved as well, and we're again going to get a new set of critical welds. And notice that when this happens, critical welds found in the previous designs need not be fixed throughout the entire optimization, so the critical welds are constantly being updated as the optimization progresses. Again, we'll solve design 3 and get a result for design 4. This is going to have, again, a combination of critical welds and welds from the spot weld lines. In this case, we're going to get 6 critical welds marked and use those for our next design. So here we start to see a non-uniform distribution of welds develop due to the combination of the critical welds that are being marked and the welds that are being created from the spot weld lines. This process is going to continue until an optimum design is found. The results of our case study showed our best design after 77 simulation runs had a reduction of 270 welds, or roughly 4%, without violating our set constraints. This design is reported in the OptimWelds interface, but there are other statistical tools within LSOP that may be used to examine the optimization results. Through the scatter plot, designs can be compared against each other to better visualize their relative performance. We've also developed a separate method that can be used with large MDO problems, which allows for many jobs to run in parallel in cases where the simulations take a significant amount of time. Critical weld information will again be extracted, and after each DOE, critical welds are overlaid and areas with the highest density are going to be marked. New condensed welds will be created in these locations for the next iteration's designs. Each design is going to have the same condensed weld locations, but different weld spacing provided by the optimizer. A major benefit to using OptimWelds over traditional weld line optimization is the ability to find an optimal solution within the product development cycle. Our traditional line optimization for our case study model, which contained over 1,000 spot weld lines, would need thousands of simulations to converge. But because our method groups lines together to reduce design variables, we needed fewer than 100 designs. This results in a significant time savings for tight development schedules. To conclude, our case study has shown the effectiveness of the OptimWelds process to perform an MDO to find an optimal, non-uniform distribution of welds. We were able to achieve this with much fewer simulations compared to other methods, which saves a significant amount of time. If we use our 270 weld reduction as a real-world example, the yearly cost savings can be roughly $3.5 million. Thank you for watching.